The procedure in sketching a curve holds the same even when parametric equations are involved. Check how it is done here in differential calculus. What are parametric equations? These are equations or functions which are written as a function of another variable. For instance, we have x as a function of t, and y also a function of t. The variable t is called parameter, and in parametric equations, the usual parameters used are t and theta. Let's have an example. Say x is equal to t, then y is equal to t squared. Let's use a table to find values of each variable. Take note that t is the independent variable, and both x and y are the dependent variables. Assuming t of -3, x turns out as -3, and y is 9. When t is -2, x is also -2, and y is 4. At t of -1, x is -1, and y is +1. At t of 0, x is 0, and so is y. Then when t is 1, x and y are also 1. At t of 2, x is 2, and y is 4. And if t is +3, x is 3, and y is 9. Connecting the dots in the Cartesian plane, we can identify the curve. So what exactly should we do to sketch curves from parametric equations? First is to take the first derivative dy with respect to x, after which we equate this ratio to 0 in order to identify t, which in turn should be plugged into the individual parametric equations in order to identify the critical points. After learning the important points, we then distinguish if they are the highest or the lowest extremes on the curve, and that is done by taking the second derivative of y with respect to x, which would be checked with the following conditions. First, if the second derivative is less than 0, or say it is negative, the critical point is a maxima. If y double prime is more than 0, the critical point is a minima. And yet, if the second derivative turns to be 0, or there is no clear answer, that means that the second derivative test failed. And if this happens, we can always revert back to the first derivative test. The first example involves the parametric equations x plus 1 plus t squared and y as equated to 4t minus 3. To start off, let's take the first derivative of these functions. First is x of 1 plus t squared. Wherein taking the derivative, it is noted that d over dt will have to be distributed among the terms, making dx over dt as 0 plus 2t with dt over dt from chain rule. Again, dt over dt is 1, which simplifies dx over dt as 2t. Next is y, which is 4t minus 3. Distribute d over dt among the terms in the binomial, making dy over dt as the constant 4 with dt over dt, then attach minus 0. The derivative of the constant 3, dt over dt cancels out, thereby having dy over dt as 4. With individual derivatives identified, determine the ratio of dy with dx. That is, by dividing dy over dt with dx over dt, where both dt's cancel out, and also 4 and 2 are reduced, giving dy over dx as 2 over t. The slope dy over dt will then be equated to 0, thereby making 2 over t as 0. By cross multiplication, t is then taken as 0. Knowing the value of t, we can then identify the critical point by substituting it in the parametric equations. So taking x as 1 plus t squared, where t is equal to 0, x is then equal to 1. With y as equated to 4t minus 3, t is 0, making 4 times 0 minus 3 simplified as negative 3. Thus, the critical point is at 1, negative 3. After identifying the critical point, we figure out if it is a maxima or minima, and that is done by taking the second derivative of y with respect to x. But since the function is still in terms of t, we can just differentiate the function with respect to t, making d squared y over dt dx is the derivative of 2 times t raised to negative 1. This procedure can shorten the differentiation instead of using quotient rule. This is then constant 2 times the exponent of negative 1 with t raised to negative 2, again attached with d of t with respect to t, which then eventually cancel out to 1, which makes the second derivative of y with respect to dt over dx as 2 over t squared. Now eliminate dt by multiplying the reciprocal of dx over dt, that is 1 over 2t. This makes the equation the second derivative of y with respect to x, which is then simplified as negative 1 over t cubed. Now let's test the second derivative by plugging the value of t, which is 0, making d squared y over dx squared as 1 over 0 cubed, making the whole derivative as indeterminate, which means the second derivative test failed. So the other option is to use the first derivative test. This is done by drawing out a line labeled as t, which is 0. Using this table, assume values of t from both sides. Say t is equal to negative 1. Plug this value into dy over dx, which is 2 over t, making it 2 over negative 1. Thus dy over dx is negative 2. A negative slope rises to the left. Do the same on the right side. Assume t as positive 1. So dy over dx is then 2 over t, which is then 2 over positive 1, or 2. The slope now rises to the right. So from the illustrations, we can then deduce that the critical point is a minima.